It's great to have Ola today. And I guess let me just introduce Ola briefly, although I think everyone knows Ola already. So as we all know, Ola is a faculty at EPFL in Switzerland, and he has written a number of breakthrough results, right, ranging from approximation algorithms, parallel algorithms, and online algorithms. And he won quite a number of awards, Hilt Prize recently, for example. And if I count correctly, 3 best paper awards at Fox and Stock. And so I guess today Ola will tell us about some of the secret techniques for these prize-winning results, hopefully. And before we start, let me remind you that if you have questions, you can type in the chat box or Q&A box. And if you want to be on the stage to ask Ola yourself, then just let me know. And I guess the floor is yours, Ola.
Okay, thank you very much. It's a pleasure to be here. So as Danupan said, yes, please feel to interrupt. I cannot see the chat anymore, but Danupan promised that he would forward the questions. So this title is pretty general. So Danupan was kind enough to invite me like 2 years ago to talk about this in a summer school. So I had more time, but then the pandemic hit. But then Danupan was kind enough again to invite me to give this talk instead. So of course, yeah, this is a huge topic. So many books have been written about this, and what I will do here is to focus, on some techniques that have been useful into results of mine. So basically, in the first part of the talk, we will look at matchings. And I will give you my favorite proof of the description of the perfect matching polytope and how that has helped us give us some deterministic progress on deterministic algorithms, parallel algorithms for the matching problem. And I also have some open questions here that I personally find very fascinating, that where we don't have a good understanding. And then in the second part of the talk, we will look at another polyhedral structure called the uncrossing that was actually useful both for the matching result and for later progress on the traveling salesman problem. In particular, we will look at, if you want to solve general metrics for the Tsp problem, then how general are actually these metrics? All right, so let's start with divide and conquer and matchings. So the perfect matching problem, or the matching problem, we are given a graph, output the matching of maximum cardinality. So here we have a matching of cardinality 3, and it's a perfect matching because every vertex is matched exactly once. So this is, of course, a special problem in computer science. Here we have a picture of Jacobi, who's credited for solving the bipartite case, and here is Jack Edmonds that solved the general case in 1965. That paper is also often credited in introducing the idea that polynomial time somehow corresponds to efficient. So since then, we have liked to use the matching problem in various models of computation. And as I said, we will look at parallel algorithms. Okay. And yes, as a side step, I would like to motivate, of course, the matching and parallel algorithms both make sense, but the problem we're going to consider also, is motivated by kind of a fundamental question in complexity theory, namely, does randomness significantly speed up computation? And if you have not read any complexity book and see this for the first time, it's tempting to say yes, because, we have many problems that we only have randomized algorithms and no deterministic ones. One example is polynomial identity testing. So you can think of given a polynomial concisely described, test whether this polynomial is identical to 0 or not. So think of a determinant over variables, for example. And here there is a randomized algorithm. Just substitute the variables by random values and calculate the determinant. But we do not have any deterministic, even sub-exponential time algorithm. However, if you took your complexity class, then you know that actually we believe that anything that we can do in randomized polynomial time, we should also be able to do in deterministic polynomial time. So particularly there is one such indication is a beautiful result by Impagliazzo and Widgerson that says if SAT cannot be solved by sub-exponential circuits, then any polytime randomized algorithm can be made a deterministic polytime. Okay, So basically, the belief is that all efficient computation can be de-randomized, but we are far from there. So there must be a lot of beautiful algorithmic techniques to be discovered. Okay, and one such situation is for the matching problem when we are interested in parallel algorithms. So here, parallel is like extremely parallel, meaning that we want to run in polylogarithmic time, and we allow a whole bunch of processes, polynomially many processes. And one of the question here is whether matching can be solved in and C-call. Okay. And if we allow randomization, then we have known for quite some time that we can solve it in parallel. So this is an algorithm by Lovatt from 1979 for the decision version. And in fact, the search version in parallel is harder. So it was first a decade later by first Kapp, Uffal, Widersen, and then by Mulmuley, Vazirani. Okay, so if we can de-randomize efficient computation, then we must be able to find a deterministic algorithm, at least for parallel algorithm for matching problem for this specific case. Okay, so that's the question, and we know for quite some graph class, I don't expect you to read all this, that in fact we can do it deterministically, but it's not even known for a pretty basic graph class such as bipartite graphs. Okay, so that's a little bit depressing, but there was a beautiful paper that made huge progress by Femer, Goyer, and Tirov from 2015 that actually showed that yes, we can do bipartite perfect matching almost in parallel, so quasi-NC. This means that it is very efficient polylog in time, but instead of using polynomially many processes, we use quasi-polynomial processes. Okay, so I want to describe a little bit just on a high level what their insight is, and then how polyhedral techniques helped in generalizing this result. Okay, so if we want to obtain a deterministic algorithm, parallel algorithm for matching problem, well, we have randomized algorithms, so a natural approach is take one of those and de-randomize it. Okay, so now let's look at a randomized algorithm, and maybe the first one you should think of is the one that the Lovatt came up with. And that goes back to the TAT matrix. You don't need to, it's not so important what this matrix is, but whatever. So TAT in 1947 proved that this matrix here, where we have a variable for each edge, is the determinant of this matrix is a polynomial that is identical to 0 if and only if G has not a perfect matching. So in other words, the determinant is not identical to 0 if and only if G has a perfect matching. So all we need to do in order to decide if a graph has a perfect matching or not is to understand whether this polynomial is identical to 0 or not. Okay. So here's an example of the matrix. And how do we do that? Well, I said already in the introduction, the natural approach is just substitute in by random values and solve the determinant. Okay. And Sankey proved in 1976 that, hey, in fact, the determinant over a field can be calculated in parallel. Okay, so that's the first randomized algorithm, which is basically Lovatt's algorithm from 1979. However, there is the second algorithm by Mulmuley, Vazirani has a very nice structure that allows us, that is a little bit nicer when you want to get a deterministic algorithm. It's maybe less straightforward to come up with, or it is less straightforward to come up with, but at hindsight, it is great. Okay, so here is their algorithm. So for each edge, just select a weight from 1 and n squared at random. So that's very much like before. But instead of replacing each variable in the TAT matrix by the weight, we replace it by 2 to the power of the weight. Okay. So here it's important that the W's are polynomial bounded. Okay, that the weights are polynomially bounded because we have the index exponent here. But otherwise, it very much looks like the previous algorithm. Okay. But the nice thing is that now, we only have this randomized step, and now step 2 is guaranteed to work if the weight function is isolating, meaning that the weight function that we selected has a unique min-weight perfect matching. So if we know that the weight function we selected has unique min-weight perfect matching, then we are guaranteed that our algorithm will work. So it's a very nice, property that guarantees the success of a randomized algorithm. And they complemented this with the step 1, right, and show that, hey, if I select my weights at random from a large enough set, then the probability that my weight function is isolating is large. Okay, but since I have such a nice guarantee for when my algorithm works, this is, in order to de-randomize something, we only need to be able to construct such an isolating weight function in parallel. Okay, so this makes, it seems a little bit hard to just from scratch design a parallel algorithm for the perfect matching problem. So now what we know is, in fact, to design a parallel algorithm for the perfect matching problem, all we need to do is to design a weight function so that the mean weight perfect matching is unique. Okay, so that's our challenge. On input G, construct an isolated weight function in parallel. And the beautiful proof of Fenaguri and Tiraf, one of the main insights, in my opinion, is, we usually tell our students that greed is good and so on, like in this Wall Street movie. But if you have seen the end of this movie, so maybe they saw the end of this movie, you realize that, maybe greed is not the way forward. And that's actually one of the insights in their paper is that, hey, instead of constructing an isolating weight function immediately, let's do it in steps. And on a high level and from a polyhedral viewpoint, the proof works as follows. Okay, so let's look at the perfect matching polytope. So each vertex here corresponds to the different matchings of the graph. So this graph had 6 perfect matchings. And now, if I want to select isolating weight functions, I would like to select a weight function so that if I optimize over this weight function, the optimal solution is unique. Now what they do instead is, hey, let's select one weight function, W1. Let's optimize over this. Maybe it's not isolating, but I will have the optimal solution will be a subphase in this polytope. So maybe it's this F1. So now the optimal solution is these 4 perfect matchings here. Okay, so I was not isolating already. So let me select another weight function and stick on this phase and optimize that weight function on this phase. Okay, so let me select W2. And I optimize in this phase. Now again, maybe I'm not isolating, I get a sub phase with more than one matching. So let me select one more weight function. Okay, so here I have 2, I select one more weight function, and now I have a unique solution. Okay, perfect. So after selecting 3 weight functions and lexicographically minimizing them in the polytope, I will get to a unique point here, F3, that is only a single matching. So now, if I lexicographically minimize W, I actually have an isolating weight function. Now, in order to get a good guarantee here, I would like to select like to prove that I only need to select few weight functions in order to get to an isolating set. Okay. And what they prove is that they only need to select log and weight functions from a family of polynomial many weight functions. So this means that we have n to the power of log n weight functions to think about in total. So then they just try all in parallel. Okay. And the key insight or key property that they use to prove that they only need to select log and weight function is that they can show that the girth doubles in each every step. Okay, so let me explain what that means. So we start with so let me draw this. Okay, M1, M2, M3, M4, M5, M6. So initially, we look at the graph with an edge set that is equal to all the matchings. And it has some girth. Okay, girth means the length of the smaller cycle. Then after I optimize W1, they show that we can select W1 so that the graph corresponding to the phase F1, which is edge set M1, union M4, union M5, has at least double its girth. So we started with a graph, it was bipartite, so it had girth at least 4, but now the graph corresponding to this subphase has girth at least 8. And then when I selected W2, I can select W2 in a way so that the girth has doubled to 16 and so on. And I can do this at most log n times, right? Because the girth can never be more than the number of vertices n. Okay? So they have this very nice progress measure of the girth, and what allows them to have this progress measure is the very nice structure and simple structure of the bipartite matching polytope. Okay, so maybe remind yourself that the description of the bipartite perfect matching polytope is just that each vertex should select one edge of degree, exactly one edge. So each vertex should select exactly one edge. So now one can see that, hey, if you know a little bit here, but for the talk, if you a little bit lost, it's not done. But now you can see that, hey, to get a phase of the bipartite perfect matching polytope, all you need to do is to set some edges to 0. In other words, it corresponds to removing some edges. So each phase here will correspond to a subgraph, and that's what they prove to show that the graph doubles in each step. However, the perfect matching polytope, the description of the perfect matching polytope with general graphs is like exponentially hard in some sense because we have exponentially many constraints. So for each set of an odd number of vertices, we say that, hey, at least one edge must go out in a perfect matching. And Edmonds in 1965 proved that this is a good this is a description of the perfect matching polytope for general graphs. However, this turns out to be a real trick, make our life much trickier in the sense that, hey, now actually the proof for the bipartite case does not work anymore. In particular, the graph progress measure fails even for very simple graphs, such as the one I depicted here. Okay, so now I would like to give you a high-level overview of how somehow, even though that this looks complicated here, how can one transfer the techniques that were developed in the bipartite case into the general case? And to do that, I would like to give you my favorite proof that this of the description of the perfect matching polytope for general graphs. Okay, so this is, I guess, one of two proofs I wanted you to understand in this lecture. So this, I don't know if you have seen it, but I think it's a beautiful proof. Okay, so I want to prove that here, this description here has no fractional extreme points. Okay, so consider the smallest graph, G, the fewest number of vertices, that for which this does not hold. So not that, for which not all extreme points are integral. So consider the smallest graph G so that there exists a fractional extreme point X star. Okay. Now, case 1. If there's no odd set constraint tight, so if none of these red constraints are tight, well, then between friends, we're in the bipartite case, right? These guys were not even used, so we have only the constraints that were present in the bipartite perfect matching polytope. So you can just reuse the proof you have seen in algorithms class for the bipartite case to prove that then, in fact, X star must be integral with the contradiction. Otherwise, there must be some tight odd set constraint that is non-trivial. So we have some set S here that has size at least 3, and also the complement has size at least 3. Okay, and it's a tight constraint, so that means that fractionally there's exactly one unit crossing this cut, defined by S. So now what can we do? We have this set. Now I obtain two different graphs by contracting. On the left, I contract the complement of S to one single vertex, so to obtain G1. And on the other graph, I can contract S to obtain this G2. Okay. So I start with my graph with a tight cut. I just obtain two smaller graphs by contracting both sides, one side at a time. All right, so notice that G1 and G2 are smaller graphs than G, right? Because each of these sets were size at least 3, and I contracted them down to a single vertex. And I selected G to be the smallest graph for which there was a fractional extreme point. This means that this fractional solution here must be able to be written as a convex combination of extreme points which are now integral. So in other words, I can write this here as a fractional solution. In this, I just made a simple case. So, for example, this fractional solution here can be written as the green matching plus the orange matching over 2. This holds because these are smaller graphs, right? And I took this, G was the smallest graph for which there was a counterexample. Now G2, for the same reasoning, I can write that fractional solution as a convex combination of perfect matching. So maybe the red perfect matching and the pink-purple matching. Now, how do you think I finished the proof? So I have a convex combination of perfect matchings in G1 and convex combination of perfect matchings in G2. Notice that each one of these perfect matchings have to select one edge here. So the green perfect matching selects this edge and the orange this edge. And here, the same. They have to select exactly one here, red and purple. Up here in the original graph, this guy corresponds to the green edge in the left graph and the red edge on the right graph. So basically, I can glue these matchings together to write X star as a convex combination of perfect matchings. So basically, X star is in this case equal to, what is it? It's the green perfect matching union the red perfect matching, the indicator vector of that over 2 plus the other one. Now I'm running out of colors, but it's M2 and M4 over 2. Okay, so that's the end of the proof that, hey, I can write the perfect matchings as a convex combination on the left and on the right, and then I can glue them together to get a write X star as a convex combination of perfect matchings in the original graph. And you know, I cannot write the I cannot write an extreme point as a convex combination, so this is a contradiction. Any questions on that? So that's the simplest proof of the perfect matching polytope that I know, and I think it's quite nice. I know I read it somewhere, so I excuse myself that I forgot who to credit, but if someone knows, let me know. Okay. So now what's the takeaway message behind this proof? Okay. Well, one is the following. Whenever we have a tight odd set constraint, if we fix an edge crossing this cut, we know that any perfect matching that is in this phase should cross this cut exactly once. So once we fix the edge, we have a unique solution. We have decomposed the solution. We have decomposed the instance into. So let me fix this edge. Now we have decomposed our instance into a unique. How to say? Independent instance on the left, because I need to find a perfect matching of the remaining vertices on the left. I don't care how you do it, you need to do it. And independently, you need to find a perfect matching on the right. Okay, so whenever we have a tight odd set constraint, fixing one edge crossing this cut leaves two independent instances. So in fact, these exponentially many kind of dangerous looking constraints, they are best friends for devising divide and conquer algorithms. Okay, and this gives you kind of a framework in the sense that, hey, do the bitype proof, and when you have an odd set constraint, do divide and conquer. And this is the route we take to generalize the result by Fenner, and Tira from bitype graphs to general graphs. Okay, so basically we get the same result for general graphs. And on a high level, also it's used by Anari, Vatsarani, and Stankowski to show this very nice result that actually we can find a perfect matching in planar graphs in parallel. Okay, so this was actually, so I'm, of course, I don't want to upset, so I'm comfortable in oversimplifying my own result, but I shouldn't oversimplify others' results. So this was, 30 years after this result was known for bitype graphs. So it's, maybe I oversimplified a little bit. And in particular, both these results also heavily rely on another structure result of the perfect matching polytope, namely the laminar structure phases. So this will be important. This structure, laminar structure phase, will be important for Tsp. So I will prove it there instead of here. Okay. So other results following FET was, they also de-randomized isolation lemma for matrix intersection and for totally unimodular polytopes. And what can be said by all these results is that we have an excellent understanding of the associated polytopes. So let me now raise two open problems that I find very fascinating. And unfortunately, I don't know how to solve them, of course. So consider an n by n bitype graph with polynomial edge weight. So here's an example. I have edge weight 1, 2, 2, 3. Now, there's the exact matching question. Is there a perfect matching of weight equal to W? So this small example I gave you has two perfect matchings. Both have weight 4. So the answer is yes, if and only if W is equal to 4. Okay, so that's a question. It basically combines subset sum with a perfect matching question. Another one is top K matching. Okay, instead of finding a max weight perfect matching, find a perfect matching that maximizes the weight of the K heaviest edges. So let's look at the example where K is equal to 1. Then there is the red matching. Well, I'm only interested in the heaviest weight in this case, so it has weight 3. And then there's the green matching, and the heaviest weight here would be 2. So the red matching is preferable if K is equal to 1. So both these questions can be solved in parallel even for general graphs if we allow randomness. But we don't have deterministic algorithms that run in polynomial time. Even so, there's parallel randomized algorithms, but not even deterministic polynomial time algorithms. In fact, the best algorithm that I know that runs deterministically is trivial. So it runs in Polyan and choose K times. I just guess the K edges that are interesting. Ooh, sorry, that I don't even know for the exact matching question. That I know for top K matching. And like my hope is to use this idea by Fenaguriotirov to get at least quasi-polynomial time algorithms for these problems. But a major issue is that we have not a good understanding of the polytopes. So I think one interesting intermediate step is to understand what is the extension complexity for these problems, even for bitype graphs. Can we write down small polytopes for these problems, even for bitype graphs? Danpam, you have a question?
Right. Oh, no question so far.
All right.
Yeah. Just.
So then I want to go to this uncrossing technique that I will explain, and the Laminar sets that I will explain in the context of Tsp. So maybe I had a question to you, but now Danapam has to answer. What is the shortest way to visit all 24,727 pubs in the UK? Well, do you have any guesses?
No idea.
No intelligent guess. I don't know neither, but it's 45 million, around 45 million meters. So this was actually solved exactly by Cook et al. In 2015. Okay, so there's Tsp, find a short tour that visits n given this, as I explained in the previous slide, it's a very important benchmark problem. So I will be, there's two basic versions: symmetric, distance from U to V equals distance from V to U, and distance asymmetric, the distance do not need to be equal. So I will be concentrating on, so here's asymmetric, sorry. And here is a tour. I will allow you to visit a vertex many times. This is equal to the metric case, okay? So basically we want to find a connected graph that is Eulerian, so that the in degree is equal to out degree. And this, if you write down the constraints for connectivity and for linearity, you get the standard LP relaxation, okay? So you have a variable xuv. You should think of the number of times we traverse the edge uv. Now we want to minimize the total cost, so we sum over all the edges, the weight of that times xuv. We want the out degree to be equal to the in degree for each vertex, so Eulerian, that's the Eulerian constraint. And then we want the connectivity, and the way we implement this is to say for every set S, we should have at least two edges crossing that set. Okay, so just notation for a set S, delta plus is the set of outgoing edges, delta minus is the set of incoming edges, and delta S is the union. So, in any tour, we should have the same number of edges going out as going in. And we should at least, for each set, we should at least enter and exit once. So we get that the total number of edges crossing that set is at least 2. So you can see that these constraints look very similar to the perfect matching polytope. So, except that we have a 2 and it's for every set instead of only for odd sets of 1. And the question here is, what's the strength of this linear program? And this has puzzled with for decades, and the state of the art is actually as follows. So there's been some very exciting recent progress. So for general metrics, there is a very recent paper by Colin Klein and Ola Svensson, who actually beats Christophilus for the first time, 3/2 minus epsilon. And first they beat it with respect to the optimum, and recently they also prove it with respect to this relaxation. For the symmetric version, there's a 22 approximation by Wiegen and Traub from 20. And you can see here, I also wrote something about unweighted shortest path metrics because there is better results known and they are believed to be the hardest instances. And also a question we will ask ourselves is how general are in fact general metrics. So for unweighted, Seb and Wiggen got 1.4 in 2014 for symmetric, and we got 13 for asymmetric. Just to make sure the conjecture ratios here with respect to the LP is 4/3 for symmetric and 2 for asymmetric. Okay, so we have not a tight understanding yet. So now I want to somehow, with polyhedral arguments, I want to understand how general are in fact general metrics. And to understand that, we will use the uncrossing technique that has been very successful. And to do that, I need to define to you what a Laminar family is. So a family of sets is laminar if every two sets are either disjoint, for example, this set here is disjoint from this set, or one is a subset of the other. So for example, in this case, this set is a subset of that. And a fact is, you can prove it by induction, is that the laminar family contains at most two n- sets, where if it's subsets of vertices, so n vertices. Okay. And now I want to prove you the second proof I want to give today. And that is if I consider an extreme point to forget about this for a moment. Okay, so if you consider an extreme point to the standard LP relaxation for Tsp, let's look at this only these constraints at the moment. So for the symmetric variant, so if I consider extreme point, this is exponentially many constraints, right? Tons of constraints. But if I consider an extreme point to this, the set of tight constraints in fact form a Laminar family. Okay, so in fact only two n-1 tight constraints. So I added this here to make my life a little bit easier. You can think of letting epsilon go to 0, then we get the other relaxation back. Okay, but if I have this epsilon size of set, then in fact the set of tight constraints is a Laminar family. If I don't have that, then the set of tight constraints is spanned by Laminar family. We just introduce a little bit more notation. Okay, but I want to prove this statement here. If I look at an extreme point to this polytope, then the set of tight constraints form a Laminar family. Okay, so it's one page proof. So one slide proof. So not one page in the like 10 font. One slide proof. Suppose towards consideration that exists a set A and B that have a non-trivial intersection and both are tight, meaning that x star delta A is equal to 2 minus epsilon A and x star delta B is equal to 2 minus epsilon B. Now, what kind of edges are there here, right? There is the edges leaving A, there's the edges leaving B, there's the edges going from A to B, edges going from A to B, that way from the intersection, and then the edges going like that. Okay, so that's the different kind of edges we can have with respect to these sets. So now we can observe that x star delta A plus x star delta B is greater or equal than x star delta A set minus B plus x star delta B minus A. All right, why? So let's look at this here. So let's look at, for example, this edge here. Okay, that edge is counted twice here. It's counted one in the cut of A, once in the cut of B. Here, it's not counted in A minus B, it's not counted B minus A. So this edge is actually not counted at all on the right, but twice on the left. Now look at this edge here. How many times is it counted on the left? It counts one for A, one for B. So it counted twice on the left. Now if we look at A minus B, well, yes, then that edge is counted once. And if I look at B minus A, then that edge counted once. So that edge is counted equally many times on the right as the left. But for any two, we count it at least as many times on the left as the right. Okay, but now we have our contradiction. So this leads to the following contradiction, right? So I have 2 minus epsilon A plus 2 minus epsilon B is equal to x star delta A plus x star delta B. Okay, because they were tight. But this, by observation, this at least x star delta A minus B plus x star delta B minus A. But this is a feasible solution, so this must be feasible, right? So this is at least 2 minus epsilon A minus B plus 2 minus epsilon B minus A. Okay, but you know, now minus epsilon A minus epsilon B, that's more negative than over here on the right, so this is a contradiction. So that's the whole proof. Okay, so this means that in our extreme point, we cannot have two tight constraints that have a non-trivial intersection. This means that our family has to be laminar. Okay, so that's just a nice of writing. Any questions on that? I cannot hear you, Danapan.
Sorry. Yes. Just one question from Q&A by Andras Salamon. Why can there be edges wholly contained in the intersection? Maybe he said he's missing.
Yeah, there
something
can be
special.
edges here,
Right.
but I don't care about them because they are not cut by
That's
any
not
of the
true.
cuts that. Yes, I mean, of course, there can be a lot of edges. I just cared about the edge types that are cut by any of the sets that I worry about.
Is there any? Okay.
Maybe I hope I didn't miss some edge type.
Right. So yeah, I think he understood now. If there's any question, just type in the Q&A box and I can ask Ola now. Nope.
Okay. So then one application of this, which maybe is the first one, is okay. Let's look at the relaxation for a symmetric Tsp. Oh, okay. So an extreme point will be defined by Laminar Family. So an extreme point is defined by 2n minus 1 of these constraints. So now this in fact implies that there is at most 2n minus 1 fractional variables. So you know the support, the number of variables that take non-zero value is very limited. It's only 2n minus 1. And the total sum of these variables, we are looking for a torus after all, is at least n. Okay, so this implies that one of the fractional variables have to take value at least 1/2. So we cannot have a fractional solution where all the fractions are arbitrarily low. There must be fractions that are pretty significant. And this is, you know, the motivation behind more involved iterative rounding schemes pioneered by Jane in 2001 for network design problems. Basically, you solve an LP, find an extreme point with a large value, round it up, and iterate once you have taken that edge. And another famous example is the bounded degree spanning tree, where they get an optimum solution by violating the degree bounds by 1 by Lau and Singh. And there's the beautiful book by Lau, Ravi, and Singh about this. Unfortunately, no one has been able to do anything with such an iterative scheme for TSP. In fact, we even know for symmetric TSP that there are some edges that have integral values on extreme points, but it so far has not helped us. Instead, we're going to use it in a different way by also incorporating duality. So maybe I will skip. I'm running out of time, so maybe I will just state the property we get by this uncrossing. Okay, so instead of saying that, hey, a variable have, there must be a variable in our extreme point of large value, what we use is that complementary slackness and duality to say that, hey, our edge weights have to have a very special structure. So basically, you know, you get the general instance with no structure on edge weights. Now, if you want to solve such an instance with respect to L-carp relaxation, you only need to worry about very specific weight functions. In particular, the edge weight of an edge is equal to the value of sets it crosses in a Laminar family. So the edge weight of this edge here is just the sum of, so we have a Laminar family with weights on the edges. This is just a dual solution. And we know that's a Laminar family thanks to the proof we saw before. It's by the uncrossing. And the And by complementary slackness, all the edges in our solution have weight equal to the sum of weights of the sets that it crosses. So it's 1 plus 4, 5. And here we have 7 plus 2 plus 5, which is 14. And in fact, if the support of our solution has edges in both directions, they will in fact have the same weight. So by just using this polyhedral structure and crossing, we have simplified our work quite a lot. So instead of looking at general weight functions, we only have to worry about these very structured weight functions. And this turned out to be crucial for the asymmetric Tsp. So we had a constant factor that had a 300 that was refined by Wigner and Traub. This approach heavily relies on reusing the algorithm for unweighted shortest path metrics by using this very special structure of the weight functions. For symmetric, I'm sorry, but there has been no such interaction so far. So I find that very intriguing. It's something I'm trying to understand is if we can use this, that general metrics is not that general, to further improve our understanding for the symmetric Tsp. And then a personal favorite of mine is bottleneck ATSP. Can we find a Hamiltonian cycle with minimum max weight instead of minimal total weight? So for symmetric TSP, we have had a tight answer for that for many decades, but for ATSP, we are still not having a constant factor. And maybe my final say here is that we have been a lot of focus on this relaxation. It's unclear to me, there is no evidence that this is the best possible relaxation. So maybe one can do even better. Okay, so we have a lot of stuff to understand here. Okay, so I should summarize. So what did we see? I gave you my favorite proof of the perfect matching polytope and how it naturally leads to kind of a divide and conquer insight. This with a laminar structure led to deterministic parallel algorithms. But for some very natural variants, I would say this top K matching is very natural. We have been able to find a max weight perfect matching for quite some time. But what if I'm only interested in the max weight with respect to the top K heaviest edges? We need to use randomization at the moment. For TSP, we can consider very structured weight functions, and there is a lot to solve. But very, very impressive recent progress. Thank you for your attention. I see I 1 minute early, but there was only like a long proof.
I see. Yes. So, okay, there are some people raising hand. Nope. If anyone wants to ask question, you can type in the Q&A or you can raise your hand too. So I guess while we are waiting for questions, let me just ask you one non-technical question. So you mentioned the conjecture of 4 over 3 and 2, right, for the general case.
Yeah.
How about the case for unweighted shortest path matrix?
So for unweighted shortest path, they turn out to be the hardest instance we know for symmetric. So in particular, these 4 over 3 are unweighted. So for unweighted symmetric 4 over 3 should be the right answer as for general metrics. So that's a little bit more, the hardest instance we know are unweighted for symmetric. So no one has been able to use general weight functions to make life more miserable. And somehow we get a lot of structure for general metrics. So that's a little bit the belief is that they should not be much harder. Now for ATSP, for unweighted, I think the best integral gap is 3/2. So there, in fact, the 2 integral gap is weighted. Then if that's because of lack of imagination or for a real separation, I don't know.
So you think 3/2 is possible?
No.
No. All right.
I think 2. Like
two.
For with respect to these relaxations, then there is no indication that you cannot do better than these relaxations.
Mm-hmm. All right. Is there any other question? So I guess not. So then for people who want to ask more questions with Ola, I think we will Ula you will have time to stay around for this social session later after this, right? For
Of
some
course.
minutes, right? So yeah, you can just drop by and say hi or ask questions there as well. Otherwise, let's give Ula a hand one more time, and then we will move to tables.